I'm Herman. I'm a software engineer at Facebook, and I'm here to talk to you about what it took for us, or it's been taking for us to deploy MyRocks at Facebook. So first of all, a lot of the features and tools that we've built for this particular process, the engineers who worked on it are actually here at the conference as well. So feel free to come by the lounge afterwards if you find any of this stuff interesting and want to chat to us about it. And so first off, deploying MyRocks. The biggest part of this was like, how do we do the validation and testing? So I'll talk a bit about the data correctness tool that we built in order to handle validation, as well as the ShadowDB tool that we have as part of this process. And then I will also talk a bit about some new features that Mark had mentioned, such as bulk loading and TTL, that we added within the last year to MyRocks in order to support either requirements from workloads we're trying to go after or from problems that we found during the actual migration process. So we need to be with MyRocks. So the goal for us is fairly simple. It's to go from this picture on the left, which is a replica set that has a single InnoDB master with a couple of InnoDB slaves, to the picture on the right, which is this MyRocks master with a couple of MyRocks slaves. Except that at Facebook, because we have so many replica sets, we have to do this many, many times. And we also realize that InnoDB has been running for a very long time. I mean, it's super stable for us. Whereas the RocksDB code base, as well as the MyRocks code base, is a lot younger. There's a lot more people who are pushing development features into it. So we're iterating on the source code much more quickly. So how do we ensure that what we deploy to our production tiers isn't going to take the whole stack down? Because we want to be able to capture problems that happen. And when you deploy at a scale where 0.01% of a problem is going to happen, you're going to definitely see it within Facebook. So to back up a step, when you need to convert your instance from InnoDB to MyRocks, the first thing you have to do is convert a single instance over to MyRocks. And the way we did this was with a tool called CPSQL. You basically do a logical dump of the InnoDB instance, and you restore it to MyRocks. And so there's different variations of how this tool does this particular process. The fastest is actually just stop the InnoDB instance, do a parallel dump of all your database shards into files, copy those files over to your MyRocks instance, and then do a parallel restore backup. And at this point, you can actually checksum all of the data that's within your InnoDB instance, and then checksum the data all within your MyRocks instance, and compare the checksums to make sure that the copy that you created is exact copy of the data that you dumped. So we can do this pretty easily. However, it does take extra resources. So other variations of this, if we didn't have the resource to actually maintain the files in the middle, you can actually just pipe it from the InnoDB instance directly to the MyRocks instance. The downside is that will just take much longer to do. But it's not quite that simple. So within MyRocks, you have to specify where your indexes live. And the way you specify these indexes locations is through this comment field that we've added to the actual key itself. The reason the location of the index is important is, for example, when you have ascending versus descending scans, different column family settings will affect the performance of it. So what we need to do is modify our schema ahead of time, identify how applications are using these indexes, add the appropriate namespace, the appropriate column family to the index, and then so that when we do the transfer, because our tooling maintains the same schema between InnoDB and MyRocks, our tooling will be able to construct the same schema across both instances. And so we had to do that with the InnoDB instance. And then because our MyRocks doesn't support running both InnoDB and RocksDB at the same time, when you take this particular schema that has engine equals InnoDB and try to create that within a MyRocks instance, it's going to fail. So the way we got around this was to remove the no engine substitution flag within the SQL mode. And this will basically let us use the default engine if it doesn't recognize what the original engine is to create your tables. And so this is just one example of things that you have to do with your table schema before you convert from InnoDB to MyRocks. And so great. So now we have a tool that lets us create a MyRocks slave from an InnoDB slave. We have our schemas all set up. And we can take that slave and we can add it to the replica set and start replication from the InnoDB master. But there's a couple of problems now come up. How do you handle differences between these storage engines? Because the MyRocks storage engine doesn't have all the features that are supported by InnoDB. And more importantly, how do we ensure that the data is still correct over time? How do you validate stuff? So for runtime, when you have an application that's talking to your InnoDB slave versus your MyRocks slave, it's not going to care what the storage engine is. It's going to issue the same queries down to it. And one of the problems that we have is MyRocks does not support gap blocking. So any application that uses gap blocks would not have the correct behavior on top of MyRocks. So we added a feature into InnoDB to actually track all the transactions that were requiring gap blocks and log them through this gap block break log parameter. And then what we can do is we can go back and take a look at the InnoDB instance and see what those transactions were and then figure out what the applications were. And then change the applications to not use gap blocks. In some cases, actually, we didn't actually care that the application was acquiring gap block. Their behavior on MyRocks would have been fine. So for those particular cases, we added a per user default session variable so that if you were to connect to us using this particular user, we can turn off gap blocking for gap block logging for that particular user. And so at runtime, this is one example of how we handle things. But the more important question is, how do we deal with data validation? And the nice thing is, for every single replica set, we have InnoDB as a reference implementation. We can either use the master or the slave to compare MyRocks against. But we can't stop the InnoDB instance in order to perform a checksum because these are serving production traffic. And we don't have the resources to be able to maintain extra copies of InnoDB that we can stop to run checksums against. So how do we solve this problem? Snapshots. This is actually being used by CPScale already. What we realized was when we needed to do a backup, we added a modification to Facebook's branch of MySQL 5.6 to do a start transaction with consistent engine snapshot, and to also return back the GTID executed set for that snapshot. And the great thing about this is when you have two servers that have the same executed GTID set, they should technically be at exactly the same level of data to be returned back through repeatable read. You should see the same data whether on InnoDB or on MyRocks. So we can create these two transactions that have exactly the same executed GTID set snapshot. Then you can checksum the tables on InnoDB, you can checksum the tables on MyRocks, and compare them. And then if there's any differences, immediately alert that there's a problem, and then we have to go and investigate. And the great thing is you can run this checker as many times as you want over a long period of time to validate that your MyRocks instances are actually behaving correctly. So how do we do this? We built a tool called Data-Correctness. And every single time you deploy a MyRocks slave, you also deploy this Data-Correctness tool. And what it does is it connects to the MyRocks slave. It issues a stop slave to the server. And remember, this is early on. So this is before MyRocks is actually serving production traffic. So it's basically just shadowing all the traffic from the master. But you can stop the slave. And then on a separate connection, it finds the local InnoDB slave, connects to it, and says start a transaction with a consistent InnoDB snapshot, and records what that executed GTID set is. Then it connects back to the MyRocks slave and says, start running replication until you hit this particular GTID set. And the MyRocks slave starts to pull bin logs from the master until it hits this particular GTID set, and then it stops. And then the data correctness tool would, at that point, on that same connection, say start a transaction with a consistent RocksDB snapshot. So now we have a connection from the tool to the InnoDB slave that's at one GTID set. And then it has a second connection to the MyRocks slave that's exactly the same GTID set. And if those match, then it can tell the MyRocks slave to continue replication. So in this particular picture, all of the slaves are still running, replicating from the master, but we have these two transaction snapshots now. With it, we can, at that point, issue the queries that generate checksums across our tables to both InnoDB and to MyRocks. And because they're at the same executed GTID set, the data has to match up. And whatever results come back, we basically record in our database for future reference. So every single run that we do, we record within the database. So we can know when a problem first starts to happen. And then we can go through all the bin logs for that particular period of time and track down exactly what the issues were. As we actually found other issues within MyRocks that we uncovered, we enhanced this tool in order to track problems like optimizer stats not being updated correctly, or inconsistencies that were happening between the primary and the secondary keys. So it's actually grown a lot since the early days when we had it. The great thing about this is this particular tool scales with any number of replica sets that we're deploying. It doesn't require extra InnoDB servers to be running. And it's actually caused a lot of problems for us, especially problems where the server's been running for 30, 40, 50 days, and then all of a sudden there's this one key that shows up, which we don't expect it to show up. Regressions, as we're pushing out features pretty quickly, we constantly are running this test and making sure that we're not regressing in any way. And this has also caught unexpected interactions between different features, like bulk loading and optimizer stats, that we may not have caught otherwise. And the great thing about this tool is that for those problems that happen in the 0.01% of your fleet, when it does happen, we can actually have the tool immediately create a checkpoint on RocksDB so that we have a data set that we can go back to and analyze at a later point. And so it's been great for us to debug problems that are going on. But that was for slave testing. This particular step of promoting a slave to a master is a huge one because we only have a single master per replica set. So we can certainly run data correctness tool to compare the master to the slave, but how do you actually get master testing without promoting a replica to a master, right? How do you test it when there's only one master? And so for this particular problem, we developed a system called ShadowDB. And what ShadowDB is, it consists of both a replayer as well as a plugin that runs on the MySQL side. So on the capture side, it sits within the MySQL server. Every single time a connection is made to our server, along with the query that it's issuing, we basically capture that query and we record it within our backend service. So we basically have stats on what the connection is, what the statements are, how long it took, what the response was, the number of row counts, latency, as well as the timings of when these commands were being issued. So we are capturing this across the board for our server. And then at a later point, what we can do is we can spin up a replayer that basically reads the stream of data that we recorded in our backend service and fire it off to a test instance. And what it tries to do is it creates the same number of connections as the original production server has seen. It tries to replay the queries at exactly the same timing as the original production server. And so if you had a master test instance that you've created here, your replay can replay all the write traffic to your master instance. Even though you can't completely verify that the data of this master matches that of the original production master, you can still see a lot of problems that are happening and then figure out how to solve them. And so this particular system enabled us to test a lot of different configurations. For example, with masters, we realized that we actually saw a lot more snapshot conflicts because of how we implement repeatable read within MyRocks. And so we've had to change the server to mimic the behavior of what InnoDB does in terms of when they create their snapshots of when you can actually see a particular row show up. And so because we're also looking to consolidate our instances onto the same set of servers, we can use this to double the load onto a particular server, onto a particular slave. We can also use this to send the same traffic to two different servers that have different column family settings to see what the performance is like. And more importantly, as we deploy this within Facebook to other types of workloads, we can use this particular system to capture what those workloads are and immediately replay it to an instance. As you can see, we also combine the two testing systems between ShadowDB and the data correctness tool for verification in a tool that we can call like select correctness. And what this basically is, it's a data correctness tool pulling in all of the queries from the backend service, creating the two snapshot transactions to InnoDB versus MyRocks, and replaying all those select queries to our instances, and verifying that the data returned back from each of those queries are exactly the same. So the checksumming tool originally would do a full table scan. This does both point queries, range scans, and it actually catches problems that the full checksum might not have caught. For example, if a particular application wanted to see 10 rows and there's a slight difference in what the 10 rows are being returned back, we found problems within the boom filter within RocksDB that was causing it. So yeah. So a lot of that was on the testing side. But what happens when you need to do this conversion at Facebook scale? As I had said earlier, we have a tool called CPSQL that converts a MyRocks instance to an InnoDB instance to a MyRocks instance, and it basically performs a logical dump restore. You have to do this at least once per replica set in order to get the MyRocks instance up and running. Once you have the MyRocks instance, we actually have a tool called MyRocks Hot Backup that lets you physically copy this to another location. So future copies are pretty fast. But again, we have a lot of replica sets. We have to repeat this step many times. So our original implementation of bulk loading was to turn off unique key checking and row locking in order to speed things up when you restore to MyRocks. But there were still problems because large instances that we have still take more than 20 hours to restore. And at the same time, 20 hours of bin log entries are being accumulated. So you have to store those bin log entries somewhere, and at some later point, replay them to your restored instance. When we're actually doing the restores on the MyRocks instance, the write rates on those particular servers also go up pretty quickly. Differences in how your primary key versus secondary key ordering affects what the write rates and compaction rates are that we see within MyRocks, and those just skyrocket when you're running this particular restore. So if you had a server that had a production instance running, and you're restoring to another instance on the server, you can start to see that the other instance gets affected in terms of the I/O throughput. Latency start to go up overall. And even though you can argue that you only need to do this once per replica set, why optimize for this? We have use cases within Facebook where we want to be able to do logical shard migrations, and that leverages the logical dump restore. So even after the conversion, we can still make use of this particular technology. So what's the basic problem here? When you do a parallel restore of multiple tables into RocksDB at the same time, they all go into the mem table. And once your mem table is full, it flushes it out to a series of SST data files. So as you can see, each of these SST data files contains portions of table 1, table 2, and table 3. At some later point, compaction happens, and it reshuffles all of the table content so that they are within their own series of SST files. And that compaction process generates a lot of write I/O traffic. And because primary and secondary keys are different, your secondary keys are very likely going to span a huge range of SST files and increase your write amplification overall. So we improved the bulk loading process by adding a feature into RocksDB called the SST file writer. And what this lets you do is completely bypass the mem table and write directly out to the SST files themselves. So when you do your dump, we only have to require that the keys be added in either ascending or descending order. So when you perform your initial logical dump, specify it to be dumped by primary key order. And then in restore, you enable bulk loading, and all of the data for that particular table gets streamed directly into a series of SST files. Because these are all happening in parallel, all of the tables are getting streamed directly to their own set of SST files, basically. But we still have a problem with secondary keys, because you've dumped in primary key order, your secondary key order is going to be completely different as well. So how did we solve this issue? We took the bulk loading process and we added it to fast index creation, basically alter table add index. So what you can now do is you dump your data with the schema that only has a primary key. You restore just that primary key data to your instance. And then you add back the secondary indexes. And when you do the process of adding back the secondary indexes, you pull all your data out from the SST file. You sort them temporarily in a series of temp files. And then you perform a merge sort of the data within temp files directly into a series of SST files for the secondary indexes. When we actually implemented this and ran this in production, we cut the bulk loading time down by 80%. So that which took about 20 plus hours to run now took about 4 to 5. More importantly, we decreased the amount of time, we decreased the write rates for our instances down by 80% as well. So this actually saves a lot on I/O throughput. You impact the other instances a lot less. And this is one of the problems that actually showed up while we were trying to do migrations, and so we put an effort to actually make this much better. And so, Mark had mentioned other features that we've been working on, namely time to live. Because there are certain workloads that want to be able to add data to your tables and then say, I want this data to expire after 30 days. So one very easy way of doing this is to add a create time column to your table, create that as an index, and then have some sort of background process that is issuing out delete queries to your table. It says delete everything older than 30 days ago. The downside of this is you obviously need space for that secondary index. You need CPU to process the delete query. And you also introduce delete markers into all of your indexes that also have to be processed. And so we can leverage RocksDB to handle this better. We already use a compaction filter for a fast drop table. So currently, if you wanted to do a drop index or a drop table, you tell RocksDB, I'm going to drop a table. We immediately come back and say the table's been dropped. The actual data doesn't get removed until the compaction filter is running on those particular SST files, at which point they get filtered out. So we can do something very similar with TTL. This is currently a work in progress. There's only support for primary-only key tables because when you have secondary keys, things get much more complicated. We support both implicit and explicit timestamp. So if you don't specify a column for your timestamp field, we'll just insert whatever's current time is. If you do have a column that you specify as the explicit timestamp, we take that value and we basically copy it over. And that could be very useful if you want to be able to migrate your tables across instances and preserve the expiration time. So at a slightly lower level, what we do is we actually modify the key value format. So we actually insert a field into the value that is the TTL field. So the first row is basically the implicit, where we just insert whatever the current timestamp is. And then when the compaction filter is running, it checks to see what this timestamp is, compares to the expiration time, and may or may not throw the row away. The second one, you can see it took the value of 14.9 billion, which is the timestamp, and copies it into our own timestamp field. And then we actually use that for the lookup process. And so there are some caveats here. Because the compaction filter is running in the background, if your transaction sees a row, it's a chance that the compaction filter may have removed it. And so if you go back within the same transaction to look up that row, it may be gone. So to kind of resolve around these particular issues, we only remove rows that have expired after the oldest snapshot has been created on the database. And we also try to filter rows so that any rows that's expired after your snapshot, you actually don't see, to prevent this particular problem from happening. And so, and then lastly, there were certain workloads that wanted to be able to have a per-partition column family support. So I already mentioned that for any kind of table that you have with indexes, you can specify which column family that those indexes live in. You may have certain workloads that you want to be able to split. So in this particular sample, suppose you wanted to partition based on the year of your data. Everything older than the year 2000, you want to have live within this certain column family that have these really high zlib compression settings. Anything less than, anything greater than year 2000, you may want to have in a separate column family that has, slightly less space efficient compression, but not as CPU intensive. So we can actually specify that now. And so. And that's more or less it. So we're on GitHub, MySQL 5.6. The current branch is based off of 5.635. We welcome anyone to contribute, or if you find issues, file issues on GitHub. Welcome all feedback for it. And yeah, if anyone has any questions, I'm happy to answer them. So, yeah.
Your ShadowDB tooling, is that something that there's any plan to put on GitHub or share in another way?
Unlikely for now. And so, because the replayer side uses a lot of the libraries that we have internally. And so the plugin side also uses some of those libraries, so it makes it challenging. But yeah. Yeah.
I think Percona had a Java-based shadow-like tool at one point.
Mm-hmm.
Do you know anything about that?
I'm not as aware of what that is. And so, but the one that we have is also based on other plugins that have existed outside of Facebook. But we integrated that support into our backend service so that we can deploy this to any number of replica sets and then be able to store that data and then replay at a later point.
What is it based on?
So MySQL actually has an audit plugin feature. And that is already capturing. So we built a plugin that uses that similar API. And so if you're interested in that particular feature, the engineers who actually worked on it are here as well. So, and it's been a great tool for us in terms of like being able to just not just capture the social graph data, but other working sets as well. And so, any other questions? All right, thanks everyone then.